on this block, I want to use the concept of the transfer functions and to explain the same thing like that. And actually, you can find the transfer functions concept a little bit easier to understand. So maybe at this moment, you can take the time to help yourself review for the transfer functions. Okay. So I would say this is the method 1. This is method 2. Okay, so method 2, and recall in chapter 3, transfer functions method. And this method basically is for this system, mx double dot plus cx dot plus kx. And the same thing here, for example, we consider is the f now and have the phase angle omega t. Okay, so basically this one is the form f now e I omega t. Okay, so that is signal like this. In the transfer function method, we have is this. This is our system. And this is our input. And this is our output. Basically, output is our steady state response. And the input is our force. Okay, the systems, we know that is m squared plus cs plus k. Again, this has been summarized in the first 2 or 3 pages in our homework 6 or 7 after that. Okay, so basically that is the whole thing described there as summarized here. So for this case, we replace s by j omega. So in this case, the m squared plus cs plus k will become, let me write down something here. So that will becomes k minus m omega squared plus j c omega. Okay? So this is a complex number. The complex number we know always have the magnitude and the phase angle. So here we define it has a magnitude called n omega. It has a phase angle and we call it phi omega. So here m omega is a magnitude and magnitude equal to this k minus m omega squared plus c omega squared. Okay, and the phase angle equal to minus arctangent minus c omega and k minus m omega squared. If you remember that one, okay. So basically here I can replace this transfer function as the m omega and with the phase angle phi omega. You good? Okay, so in this way we can put into our information here. For the input, right now we have a force that has a magnitude f naught, and we have the phase angle omega t. The output has a magnitude which is equal to the magnitude of the input multiplied with the magnitude of the transfer function. So that is f now times n omega. So that's the magnitude. And phase angle is the summations of the input plus the phase angle of the transfer function. So that phase angle equal to omega t plus phi omega. Okay. You good? If you should remember the transfer function concept, transfer function basically allow us to do the algebraic calculations of the output. Again, the magnitude multiplied together is input with the transfer function. Phase angle simply added up together. And let me implement the whole things. Basically, this one will be equal to, let me use the black color here. So basically, the output, let me implement this one. So therefore, the steady state response will be equal to F now multiplied with the M now be equal to F now and divided by this. K minus M omega squared plus C omega squared. Okay? Right now I simply plug in M omega into here, so that becomes this. And what is phase angle? Phase angle equal to omega t plus phi. So basically it equal to E times I and phase angle equal to omega t plus phi, omega t plus phi, let me plug in here. So here, set right in, let me keep this one, so phi equal to this one, okay? Let me implement this one, details. Omega t plus arctangent minus c omega divided by k minus n omega squared. You good? Okay. So here we have a minus here, so why not, because arctangent minus something equal to minus here, so why not we get a minus something over here? Good? If you compare this form to this form, they are the same. They are the same. Okay? So this is our template. So right now, keep this template in mind. Then we see how can we apply this template to the combination of the many terms. So this is our transfer functions. The system is unchanged. So that is M omega and phase angle. Okay. And right now we have an input. So let me write up the generic template. This is the input and this is the output side. So right now, for our case, we have how many terms of the input? We have an input that is, if you remember, our general is the A now divided by 2 plus A1 cosine omega t and plus the B1 sine omega t, right? And plus something something. So this one, this single term, how about this? Let me just combine it into, say, F1 times E I omega t. Okay? So then the second one is simply 2 omega t. Let me say F2 E I 2 omega t and plus F3 E I 3 omega t, etc., etc. What, okay? So basically, this representing the component corresponding to working frequency omega, component corresponding to working frequency 2 omega, 3 omega, 4 omega, etc., etc. Okay. So here we have A now divided by 2, and its phase angle basically is 0 degree. That's the phase angle, and we also have the F1. And E I omega t, and we have F2 E I 2 omega t, and continue. Let me build up this one. Continue. Okay, so Fn E I n omega t. Okay, continue. We have so many different terms. Good. Any questions? So right now we have these terms. So basically here, this representing this is the complex expression, and that has a phase angle omega t. So why not we put into the format we like easier. So if you like, you can convert it into just simply introduce that the phase angle is omega t. Okay, so what I do so is this. Again, if this is our complex plane, let me do this one more time. Say I like these numbers 3 and 4. So if we have a complex number 3 plus j4 here, okay. So this complex number basically is the phase angle. This phase angle equal to arctangent. The imaginary number divided by real numbers. I think that is 53 degrees, I think. Okay, so basically for this particular complex number, and its magnitude equal to 5, and we have a couple expressions. For this one, 3 plus j4, we have quite a few different expressions. One is 5 times the phase angle, 53 degrees. Or the otherwise, you like to express is I times j, 53 degrees. Otherwise, you like to express is 5 times cosine 53 degrees plus j sine 53 degrees. Okay, so we have a couple kind of the general terms, and right now I simply replace this e into this one, so that'll be easier for us to graphically see the magnitude and phase angle. You good? Okay. So right now we have an input. The output simply is you can visualize this is the transfer function of the system, and respond to this one. We have again the magnitude multiplied together. That is corresponding to this. That is a now 2 multiplied with m omega. Okay. And then the phase angle simply is this one added up this one. So phase angle equal to 0 degrees plus phi omega. Okay. For the second component of the input, again, the magnitude multiplied together is f1 times m omega. Okay. And then the phase angle simply is omega t plus phi omega. Okay, we come to the second one. The second one, the magnitude multiplied together is f2. This is the magnitude, okay, times m. In the template, omega represent is the working frequency. For the second component, what is the working frequency? 2 omega. So you introduce 2 omega here. Okay, so what that means, the m2 omega. So that means m2 omega using this template simply is this. K minus mu, because that's a function of omega. So right now this is a 2 omega. You simply replace 2 omega, the omega by 2 omega here. You good? Can you see it? Okay, this is important. And then the phase angle again, omega t plus the template is this is the phase angle as a function of the working frequency. So that is phi 2 omega. So again, what with this template, phi n omega will be equal to arctangent minus, so minus c times n omega, and then k minus n omega squared. Okay, so I put into general. So now continue. So for the n component, that is fn times m. So right now for this one, we have a working frequency n omega. So you replace by n omega, the phase angle omega t plus v n omega. Good. So basically the total response, the output will be summations of the whole terms. So that is the give us the steady state response of the system. Substitute this kind of the force. Okay, so substitute Ft equal to so many terms, and you can write it out. That is a combination of these terms here. Okay.